Okay, I have the top of the hour and I want to welcome everybody to the NCAT From Research to Implementation webinar series. We've been doing this for a few months now. I think we're at, what are we, Buzz, at month 7 or 8 now?
Something like that, Travis.
And so it's been really great for us, and we're excited that we have the opportunity to share this kind of information. Today, we're going to be talking about the 3/4 inch thick 4.75 nominal maximum aggregate size SMAs that have been used for some high performance preservation. And so today, as always, we have Buzz. We also have Dr. Carolina Redesno, and we have John Jenkins from Alabama DOT. So we've talked about Buzz plenty of times.
That's John Jennings, Travis.
Oh, Jennings.
I apologize.
I'm sorry, Jennings. I don't know why I did that. Sorry, John. John Jennings. I was on the fly. That's why. Okay, so we always introduce Buzz a little bit. He worked for the Alabama DOT for 12 years and then 2 years in the private sector before he became the first NCAT track manager in 1999. And now he's an associate director here at NCAT and a research professor for Auburn University. And Carolina, she's an associate research professor here at NCAT. She joined NCAT in 2011. She has more than 16 years experience working with asphalt technology. Her research expertise includes sustainable pavements, performance-based asphalt mix design, field performance evaluations of pavements, and asphalt material testing procedures. She's been able to do research for NCHRP, FHWA, NAPA, and several state DOTs. She also teaches with the university here in Auburn and assists NCAT in instructing all sorts of courses. John Jennings is a licensed PE with the state of Alabama. He's been that way for about 12 years now, before coming to work for Alabama DOT, where he works in the Bureau of Materials and Testing. He spent 4 years in the private sector doing things like site design and various types of development. He's worked with pavement design in particular for the last 12 years, and he's been the state materials engineer for ALDOT for the last 3 years. So given that, just a couple things, please put your chat in the chat box and I will help get the questions onto the folks after the end. We're going to have Buzz start off. He'll turn the time over to Carolina, and then we'll turn it to John and we'll answer any questions at the end. And as always, we work hard to make sure we end this on time and let you all get back to your busy days. Given that, Buzz, I'd like to invite you to continue from there.
Thanks, Travis. I appreciate it very much. And good morning, everybody. I would just kind of add to the intro stuff that John works over in the office at Materials and Tests over in Montgomery with Alabama DOT, where I sort of grew up professionally. I worked for 12 years over there in the same building, I think, that John is in, and he and I are friends. So Carolina and I are very, very pleased to do this webinar this morning on 3/4 inch thick 475 MS SMA preservation mixes. The flow of these webinars is usually it works out something like this. I come in and provide a little background and kind of a little bit of a track history lesson when it comes to the topic of the webinars, and then our subject matter expert here at NCAT comes in. That's Dr. Carolina Redesno, and she comes in and talks about the specific research project. And then we like to get practical with it and talk about how this mix has been used with either a private sector presenter or a DOT presenter. That's the role that John is playing today. And then typically I kind of wrap it up and we have a little bit of an open discussion about the takeaways. So, the takeaways are the important thing, right? We don't do webinars for the sake of doing webinars. We like we like to share what we've learned here so that y'all can take it and you can implement it in your practice. So this, as with a lot of things, this starts with the NCAT pavement test track. I've been really blessed to be here since 1999, actually. Travis, I've started my 24th year, which is kind of hard to believe. But when we built the first track and we finished it in 2000, it was a big perpetual pavement experiment. We had several feet of asphalt and we were studying different primarily binder layers and surface layers in combinations at the track, but it was really thick, and we really were not. It was a study of mixing materials. But beginning in 2003, we started doing different things. We ripped out our thick pavements. We started building thinner pavements, and then also in 2003, we put our first, what we now call a preservation thin lay on the track. It was a dense graded thin lay, but it was a 475 in mass mix. That the objective of it was to see, hey, will this work on kind of a high performance county road? And we really didn't. No one really had strong expectations for it. We kind of thought that it wouldn't last very long, because that sort of is our bias about the smaller mixes, that they, smaller, finer mixes might not be able to exhibit good performance. But now, after 73 million easels plus, that 2003 3/4 inch thick 475 dense graded mix is still on the track. So that's kind of where our preservation thin lay history started. Also in 2003, we did a 9.5 millimeter in mass SMA that was part of a structural experiment with thinner pavement structures, which we would call a 1 inch thick SMA, really a preservation thin lay. So the subject of this webinar is the 475 version of that mix, but we had a long-standing specification for a 9.5 in mass SMA mix in Alabama, which John, y'all specified, by max size, so that was a 12.5 max size SMA. But we've had a lot of positive experience with smaller mixes and with SMAs, and the topic at hand today kind of combines that. Well, our research program at the track, and in fact the research program at NCAT, it's very responsive to the needs of state DOTs, responsive to the needs of agencies. So where the first track was a big study in mix and materials, and then we started doing structural work in 2003, primarily for MEPDG type research. In 2012, we started doing a lot more research in preservation, because that was the big need that the agencies had at the time. And that kind of brings us up to the topic at hand for this webinar, which is 475 in mass SMAs used for preservation purposes. So I'm probably, John's head might be spinning around right now, because we talk about things in terms of in mass. But the first thing we want to do is make a note that ALDOT specifies their mixes and polices their mixes by max numbers. So when we talk about a 475 SMA, that's John's 9.5 max mix, but it's the same mix. We're just kind of speaking a little bit of a different language. NCAT did a report that was published on the NCAT website, which is ncat.us. If you go to publications and then NCAT reports, report number 03-05 is a document that describes the design process for a 475 in mass SMA. Now it's a bit of a contradiction in terms, because SMA usually stands for stone matrix asphalt or stone mastic asphalt, and a 475 mix really technically doesn't have any stone in it. It's kind of a stone less mix, but it still is. It's the same aggregate skeleton principle that you apply to an SMA, but it's just with a smaller size. So that report's been in place for a long time. ALDOT has had a specification in place for a long time, but it's not been used. And John, you can correct me when you get to your point in this, but there was concern over the value that it would provide and versus the availability of the material that it takes to run it, because that's the trick with this mix that you're going to see as we go through this, is it's gap graded like an SMA is gap graded. And when you get really small and you talk about gap grading, that's challenging from an aggregate perspective. You got to have the right rock to put this together, the right size material to put this together. So we had the process, we had the specification, and my understanding is it just sort of sat there and was not being used. But interest has grown in the use of high performance thin lays as a preservation tool. So we're doing thinner layers because we're making our dollars stretch farther, and we're focusing more on keeping a good roof on the house. So interest grew on the use of 475 as a preservation tool. And so what we decided to do, the way the track works is it's essentially a giant research cooperative. So all the different states that have test sections on the track, which there are 11 states that are actually on the track right now. About 2/3 of the states are in the partnership through the group experiments, but we have 11 states that are actually on the track. And so ALDOT made the decision, all right, let's take a look at this SMA that we've not used in the past, the small SMA. And they told us, use locally available material, don't do anything special, because we want to see what this looks like on the track, what it looks like under heavy truck traffic, and do that as a proof of concept, so that we can see, do we need to ask the aggregate industry to respond and produce this uniformly graded material that is necessary to put these mixes together. So that's kind of my part of the track background for this thing. So I'm going to stop sharing my screen, and I'm going to hand off at this time to Carolina.
Thank you, Buzz. Let me do this and make sure this is working fine. Let me know if you can see my screen now.
We're seeing it in your presenter mode, Carolina.
Okay.
So you need to swap it back. There you go. Thank you.
Okay, thank you, Buzz. Thank you, everyone, for being here this morning. And I'm glad that I was planning to give a little background of the experience that we have here at NCAT with inlays, but I think Buzz already did that for me. So it's just making my job a little bit easier here. So as Buzz explained, we have a lot of experience through the years, starting in 2003 with the construction of thin lays at the NCAT test track. So in the 2018 test track cycle, Alabama DOT once again decided to sponsor the construction and to monitor the performance evaluation of this 3/4 inch thick 475 nominal max SMA thin lay. And once again, the whole goal was to provide the DOT with a thinner high performance overlay that could provide a durable option for pavement preservation when you are dealing with high volume roads. So once again, the decision here was based on history of success that we have with other test track thin lays over the years. Something important to point out, getting into the details of the construction and the design of the section, is that in order to be able to assess the actual performance of the thin lay, it was required to, or decided to construct a structurally sound pavement underneath the structure. So before the placement of the SMA thin lay, a 7-inch asphalt base that was produced with a HIMA binder was placed and compacted in one lift beneath the thin lay, the SMA thin lay. So a little bit of information about the actual mix design. Once again, this was a 475 nominal max mix designed with a 50 blow Marshall design, or 80 pounds per square yard mix. The AC content of the mix was 6%, and the binder that was used was an SMA binder 76 - 22. The final build thickness was actually 0.8 inches. And here we have the combination of aggregates that were used. It consisted of 62% limestone, 13% granite, 5% fly ash, and then we have 20% wrap material. Buzz gave you a background about how there was a specification already in place for the mix, but it was not really used, and we didn't have any prior experience with this particular smaller nominal max mix SMA design. Something important to point out as well is that Alabama DOT does not allow the use of high percentage of carbonate aggregates like the limestone that we have in this mix when you are dealing with surface mixes. But for this particular project, the DOT decided to grant it and allow us to use locally available materials. So we were able to put this design using that 62% limestone. Just to give you an idea, and this is moving forward without me asking it. The current specification actually limits the percentage of these carbonate aggregates using the British pendulum. And just to give you for reference, this particular aggregate had a BPN 9, or the British pendulum, after 9 hours of 26. That would have limited the percentage of this type of materials or limestone to only 35%. And this particular mix has a 62% limestone. A little bit of information about the construction. We always want to see that things are running smoothly here. The section for reference was constructed on on August 29, 2018. The mix was produced at 340 degrees Fahrenheit and had an average in-place density of 93.8, which was pretty close to the target 94% density. So once again, the mix, the construction process, we have a really good day that day, and the construction process went really smooth. I'm presenting you here information about laboratory performance tests. I want to point out that this particular mix was not designed using a balanced mix, but we like to collect information about our mixes here in terms of laboratory performance evaluation. So we ran several tests for this mix. We ran hammer wheel tracking tests to assess the rotting performance of the mix. We also ran IDLCT to assess the cracking potential of the mix, and finally Cantabro tests to have an idea of the potential durability of the mix. So here I have the results just for reference. As you can see from the average hammer wheel tracking test results, 10,000 and 20,000 passes, the rotting that we got was really small, only 3.5% at 10,000 passes and 5 millimeters after 20,000 passes. We also ran IDLCT, as I mentioned before, and in this case, we ran this test on reheated plant-produced lab compacted mix, and also on what we call critically aged plant mix lab compacted mix, plant mix lab compacted. For reference, reheated is pretty much you collect the mix during plant production and you reheat it in the lab and compact it and run the tests. When we are dealing with a critically aged, we are aging the mix an additional 8 hours at 135 C. The loose mix, we age it like that to have a better indication of the cracking potential of the mix. And you can see in the screen the numbers that we got, 50.4 for the reheated mix and 21.8 for the critically aged mix. As I will mention later, we don't really have a criteria well established for SMA, but it was good for us to see what kind of numbers we will be getting, because at the same time we are monitoring the performance of this section. Cantabro was also conducted in this case, similar to the explanation that I gave you for IDLCT, even though there is not set in stone criteria. The average Cantabro loss percentage was really low, only 5.8%, which gave us an indication that it will be a durable mix. This is what we always want to see, right? When we are monitoring test section, rotting performance and cracking performance. And this is the information that I'm presenting you here is at the end of the test cycle. So the section was sponsored in the 2018 cycle, and these are the results that we got after 10 million E-cells of the section being in place at the end of the test cycle. So rotting, as you can see, very low rotting, approximately 0.1 inch after the application of the 10 million E-cells, and there was no cracking in this section. We also monitor the International Roughness Index, or IRI, at the end of the test cycle, and I'm sure probably when you see this, you are pretty surprised to see high numbers here, because these are not typical numbers, but I'm going to give you a little bit of background of why we got those high numbers. As you can see from the beginning of the cycle, we got really high IRI numbers, but this was due in part to the uneven finish of the underlying thick base that I explained before, that was placed as a one lift. I told you that we placed that layer before the actual thin layer. Just to give you also an idea, the IRI was measured before the placement of the thin layer, and it was in the range of 400 inches per mile. It's important to point out also that when we are evaluating these sections, you may know these sections are 200 feet long. So if you think about it, there was a little bit of a drop coming in and out of the section that probably inflated the results a little bit. but we consider that a 300 inches per mile is a good estimate of the actual value that we had prior to the placement of the thin layer. So we can see how the IRI actually dropped significantly after the placement of the thin layer, if we think about it like that, and that the numbers remain really stable for the duration of the cycle. We also monitor the friction or skid number using the lock wheel friction test for the duration of the cycle. Once again, 10 million E-cells. And as you can see, the numbers, we typically compare the numbers that we are getting with what we call the safety threshold of 30 that has been established at NCAT through the years. So despite the use of these high limestone percentages, we didn't have any issues in terms of friction numbers. A little bit of the summary of the findings. You have to realize this was a section that was trafficked for 2 years. So after 10 million E-cells, this section performed really well with no cracking and has indicated in this presentation minimum rotting. Also has explained previously, the IRI was high from the beginning of the cycle, but remained stable over time. And once again, this was attributed to that rough underneath base layer that was placed prior to the placement of the actual surface layer. Friction numbers, as indicated before, were above the safety threshold, and these provide an indication that despite the high percentages of limestone that we use in this design, the section had an adequate friction performance at the end of the cycle. In terms of Hamburg results, as indicated, the mix was not susceptible to rotting, and this was supported with the minimal rotting that was present in this section. The Cantabria results also suggested that the mix had an adequate durability. When we are looking at the ideal CT results as an indication of the cracking potential, although we don't have really a criteria well established for SMA mixes, the good cracking performance of this section may indicate that the ideal CT results are adequate for this particular mix. So the overall conclusion was that it's really feasible to construct this type of SMA. I'm sorry about that. I don't know why my computer is doing that. Is feasible to actually construct this type of thin layers and achieve satisfactory performance. So at the end of the cycle, it was suggested to the DOT to continue traffic to be able to evaluate the long-term performance of this section. So that was, the section was constructed in 2018. We completed the cycle in 2021, and we decided to continue traffic on this section in the current cycle. So as part of the 2021 cycle, we are, the section was left in place and is currently under evaluation. As Buzz mentioned previously, right now, today, this section has been able to endure approximately 13 million E-cells of trafficking and still has an excellent performance. And all what we have left to do is to continue monitoring the performance for the remaining of the cycle and be able to have an assessment of the long-term performance of the test section. I think that's what I have. And I'm gonna be here for any questions that you may have.
Once again, thank you for having me. And as Buzz mentioned, Alabama is slightly different than most of the world since we use maximum aggregate size instead of nominal maximum aggregate size. So this is going to be my walkthrough into the implementation of the R3/8" maximum aggregate size SMA, how we came to see a need for it, and a recent application of it on an interstate project. There is a large number of sources that go into just pavement design and asphalt at ALDOT period. There's a large number of documents that go into it, standard specifications, standard drawings, testing manual. we're not really going to focus on any of those. The ones that we're mainly going to focus on for this is going to be these three. We have the guidelines of flexible pavement design in Alabama. Alabama is one of the few states that has a design that we have approved previously through FHWA on how we will design flexible pavements in the state. We also have one for rigid as well. Guidelines of operations. Guidelines of operations are general guidelines that we want to show and how we apply projects through the construction process. The one that we'll be referencing here is going to be the one for bituminous plant mixes. And the ALDOT pavement preservation policy is an agreement that ALDOT has with FHWA of how they are going to allocate their funds and how they're going to actually use or apply any federal issues when it comes to maintenance resurfacing, any safety issues, and just scoping of projects in general using federal funds. This is a little bit on the basic side, but when we have our mix type, we divide it by traffic. ESOL range AB for us, 0 to 1 million ESOLs. ESOL range CD, 1 to 10 million. ESOL range E, 10 million to 30 million. Anything greater than 30 million falls under stonemetric asphalt. The greater than 30 million is the majority, if not all, of our interstate projects. And just as an aside, our state has kind of quit creating an AB mix by itself. Most of the mixes that are produced in that range are a CD mix that pass for everything. So we end up with an SMA mix that handles most of the larger routes, an E mix that is got a little bit more stiffness to it, and then a CD mix that is most of the state routes. Additionally, it's divided into maximum aggregate size, so that's the gradations of it. The wearing surface that gets used for most of the state routes is a super paved mix that goes down at a laydown rate of 165 to 280 pounds per square yard. It's approximately 1.5 to 2.5 inches thick. We have previously had a 3/4 inch maximum aggregate size SMA, but due to permeability issues, that has not been allowed as of recently. The mix that is used around the state mostly for all of our surface mixes is the 1/2 inch maximum aggregate size. That's pretty much every state route other than things in the southeastern section of the state where they will try a 3/4 inch wearing surface. And what we have on the majority of the basically every interstate we have is a 1/2 inch maximum aggregate size stonemetric asphalt wearing surface. The laydown rates for that go down between 1.2 inches and 2 inches. So that's all of our interstate mixes. We have had a 3/8 inch mix previously. It is used in the eastern portion of our state around our Alexander City area mainly. So we do have a thinner wearing surface super paved that we have used traditionally, and that does go down 0.7 inches to 1 inch. It's not widely used, but has come up in more popularity recently because of pavement preservation getting more of a boost, and it's been encouraged more. The mix that we're talking about today is the 3/8 inch maximum aggregate size stonemetric asphalt. Before this was done, we were unable to specify an SMA for any of the interstates less than 1.2 inches. That's why this was so important to us to kind of fill that area. And as I said, that closes a gap for us. If before we did that, it was unable for us to really have a good bit of flexibility when it comes to the interstates. Everything was going to be a basic mill and fill, or everything was going to be milling of some amount, and we did not have the flexibility to do more pavement preservation that we really wanted to. The ALDOT pavement preservation policy, I said, is an agreement mainly with the Maintenance Bureau and FHWA as far as how we allocate our pavement preservation maintenance resurfacing dollars. It's this current version was signed in 2019. We had a previous version signed in 2012. It establishes just the divisions of how we organize our projects and the safety requirements that come along with it. So there are things tied into our pavement preservation policy that determine when guardrails get updated, what cross slope gets updated for what amount of the amount of money associated with a project, and exactly what the project entails. It also lays out how we scope projects to a certain extent too, and I'll get to that later. One thing that's laid out inside our pavement preservation policy is the definitions of the preventative maintenance versus minor rehab. For our use, preventative maintenance is just basically extending the functional adequacy of pavement. It is everything that is not adding structure to the pavement. If we are doing a preventative maintenance project on a route, in some form, it should be structurally sound pavement as a whole. Minor rehab extends the useful life of pavement. We actually do have some form of increase in structure that we can add on those projects. Benefits of preventive maintenance. I'm sure most of you have heard this already. And it does kind of come back to NCAT's perpetual pavements that they have done in the past. If you apply a PM1 treatment at the proper time on an adequate to good pavement, then it can extend its service life, possibly indefinitely, as long as there is no bottom up cracking, which in general we will not have on any of our interstate projects, and it is also that way on the NCAT test track. There is an opportunity to have a perpetual pavement to just take off or deal with any surface issues, any oxidation, any top down cracking, and just continue the useful life of the pavement, possibly indefinitely. This is something you're probably not going to see anywhere. I have seen the cost per lane mile of how we handle projects at ALDOT. So this is the lane mile cost of a PM1 versus a PM2 versus a minor rehab. PM1s in general, and I'll get to the definitions, is mainly just our safety layers. It's any OGFC, anything like that. The PM2s in general are mill and fill. It is you take off the wearing surface and you put back a wearing surface. This is the majority of the maintenance resurfacing that happens in our state and in most other states. That's where the money gets spent. And the minor rehabs are the larger mill jobs. For us, it's milling of a 2 inch to 5 inches and then putting back similar to get back up to the structure that you need. So this translates into, for the money, for the lane mile cost, you can do 6 PM1s at the same cost of 3 PM2s at the same cost of 2 minor rehabs. So a single minor rehab costs the same as 3 PM1s. You can touch 3 times the lane miles doing preventative maintenance 1 treatments than you can a minor rehab. At the same time, you can touch twice the lane miles on a PM1 as a PM2. So if you are just milling and filling an OGFC instead of replacing that entire wearing surface, for our cost, we are able to touch twice as much roadway. And that gets the attention of the higher ups, and it is very, very attractive to any people controlling the maintenance funding. As I said, this is the breakdown that we have for preventive maintenance and minor rehab. Our preventive maintenance is divided up into 2 sections. We have a PM1 and a PM2. PM1s are mainly the safety treatments. They are anything that is scrub seal, microsurfacing, fog seal, chip seals, OGFCs, high friction surface treatment, but you are not adding structure. This also has very limited milling. PM2s are typical mill and fill operations. That is milling of up to 2 inches, the way that we define it and the way that it is applied. There's obviously a little bit more funding that has to be allocated for milling 2 inches compared to little to no milling that happens with the PM1. Minor rehab, as I mentioned before, is any milling of 2 inches to 5 inches, and there is an opportunity to add some sort of structure. Minor rehab is also the treatment that requires cross-slope correction for anything for the safety of the roadway. It also throws in the guardrail updates, anything that maintenance bureau has to be responsible for. That is also the only option that has continuous leveling of any kind. When reports are sent to me for pavement designs just throughout the year in general, we do allow 500 tons or so of leveling or patching, or however we need to describe it, for just the general use of the contractor to be able to complete the roadway in time. I understand there's turnouts and there's different things that come up in construction, but as long as it is a small amount, that gets through. But the only time that we really have any sort of large leveling comes into the minor rehab, because that throws the cost of the projects off. Allowable PM1 treatments, as I said, there's more than a few. Crack filling and sealing, fog seal, scrub seal, chip seal, slurry seal, microsurfacing. Some of these we use more than others. We don't really use much fog seal in the state. We do, however, use a large amount of scrub seal to seal cracks, and microsurfacing we have started using more recently after there's become more research at the test track, and we've had very good results with that on smaller traffic routes, and we even have a few instances where we have applied that on interstates and rural interstates. This is where the 3/8" SMA comes into play. As of the last pavement preservation policy that we signed, we had the thin lift asphalt concrete layer as seen that is considered a PM1 treatment. For the purpose of our design and how we allocate these projects, we do not consider that to have a structural layer, even though we know it does, but that is an agreement that we have with FHWA of how this particular document was written. So in a PM1, in the process to spread our money as much as possible, we can put down up to an inch of either super pave or SMA on top of whatever other safety layer comes along with it. So scrub seal, OGFC, Cape seal. For Alabama, Cape seal, the way that we define it, is a microsurfacing over a scrub seal. I realize that there's a few different Cape seals that NCAT uses, but this is our definition. As I said, the milling options for PM1s for us are limited. There's two different criteria: one if a safety layer is present and one if it's not. For the particular example that I'm going to give, there is not a safety layer present, so that means that we can mill up to 1 inch to remove any oxidized surface or existing traffic stripe. If a safety layer is present, then we are allowed to mill 1.25 inches to 1.5 inches. And the scabbing that's mentioned on the screen is something that is a carryover from our 2012 ALDOT pavement preservation policy, but it's not written down anywhere now. We try to prevent any remnants of a milled surface that is 0.74 inches or less after milling. So that portion right there is why we ended up seeing the need to go toward a thinner SMA, because as I said earlier, we were limited on the thickness that we were putting down the SMA or the SMA wearing surfaces on the interstates, but we still had to leave 0.74 inches minimum in place if we were going to not mill an entire layer. So that if we did have any top-down cracking, that really limited how much we could do. In summary of all this information that I've just tossed at you, it's how we make the decisions of going into a scope. Most of our interstates were 1.2 inches to 2 inches thick. If we do actually mill, we have to either take the entire lift or leave at least 0.74 left. PM1s have been encouraged from our higher ups and from our maintenance people to do it as much as possible, just so that we can stretch our dollar as much as we can. And without a safety layer present, the most you can mill on a PM1 is 1 inch deep. So Another thing that the pavement preservation policy lays out is how projects are scoped in the state. And it defines that the work of inspection is done by the region or area. That's our state is divided up into 5 regions and 10 areas. So it's done on the local level to have the people go out and do a condition survey and get the traffic and everything else. The scope team for the state routes, they're going to be mostly the region or area. And then the bureaus who kind of govern over those areas, that they come in after the fact to actually double check all the designs and everything else. For interstate routes, however, because they do need more federal oversight and because we are getting the federal money, the scope team is required to include an interstate maintenance review committee. So we have a group from the bureaus with a federal representative going around the state and actually looking at our interstates and deciding how we are going to maintain them and allocate the money for the interstate routes. Since 2019, when I came on to the Interstate Maintenance Review Committee, this is who's been on the committee. We have Scott George. He is the State Materials and Test Engineer. He is the Bureau Chief of the Bureau of Materials and Tests. Myself, I'm the State Materials Engineer. Stacy Glass, who is our State Maintenance Engineer. He is the Bureau Chief of the Maintenance Bureau. Mark Waits is the Deputy State Maintenance Engineer of the Maintenance Bureau. Our FHWA representative that comes along with it is Chrissy Harris, and she has specialized in pavement and materials for a while. This is the particular project that I've decided to reference when it comes to the 3/8" SMA. I'm going to give you a lot of the backup information as far as what went into the project, where it is, and we'll go through the decision-making process based on all the information that I just tossed at you. The scope was held in April of 21. It is located in Lee County. It is Interstate 85 from milepost 51 to approximately 56.5. The last time that it was resurfaced was in 2015. When they did that job, it was a milling 3.5 to 4 inches, and they came back with an 1.5 inch thick wearing surface on top of a 2-inch binder, both of which were SMA based on the traffic. For whatever reason, they decided not to place OGFC at the time. Field observations: the existing SMA wearing surface is oxidized. We had minor raveling, minor cracking, not too bad either way. The southbound, however, was in much better shape than the northbound. On both directions of the project, though, we did falling weight deflectometer readings that showed no need for additional structure. So we knew we were in the preventative maintenance in some way, but it was either going to be a PM1 or PM2. We did not need to have a minor rehab. We did not need to spend that money. The rutting information: there was some rutting present. There wasn't a lot. The MRI is as shown, and the traffic was not small. I mean, it was 49,000 ADT per day. The trucks per day was at 18%. So we ended up with a total easel count of 38 million easels, and that it distinctly falls into the SMA mix. Coring data: the crack depth on the southbound roadway was 1.17 inches. The crack depth on the northbound roadway was 1.8. As I said earlier, the wearing surface that they placed was supposed to be 165 pounds per square yard. That should equate to 1.5 inches, but obviously we came out with a thicker lift in practice than what was prescribed. That it ended up averaging out to about a 1.8 inch wearing surface throughout the entire project, and that's kind of how we made the decision. It was going to be 1.8 inch to 2 inches. But as I said, the northbound roadway was in much worse shape than the southbound roadway. The northbound roadway is cracked through the entire wearing surface, basically, and the southbound roadway still has some life left in it in that top layer. As I said, the northbound roadway is cracked through the entire surface. The southbound roadway is cracked, but not as badly. So we decided to use separate recommendations for each main line since it is a bifurcated interstate. So we ended up doing 2 different things to try to save money on the southbound side. The northbound recommendations, based on the crack depths, we milled the entire wearing surface down to 2 inches, and we came back with a 2-inch, half-inch maximum aggregate size SMA wearing surface, and then a 90-pound OGFC layer. 90 pounds per square yard equates to about 1 inch thickness. So we milled 2 inches, and we came back with 2 inches, and then put a 1-inch safety layer on top. That side of the roadway technically qualifies as a PM2 by our standards. The southbound mainline recommendation, as I said, the southbound roadway was in better shape than the northbound, and we decided to try to save the part of the wearing surface that was still functioning. So we decided to mill 1 inch down into the 1.8 inch to 2 inch deep wearing surface. So just to prevent any scabbing. As I said, any scabbing is anything 0.74 or less. And then we came back with as mentioned, the 3/8 inch maximum aggregate size SMA wearing surface. Decided to place it at 90 pounds, and then decided to put the same 1 inch thick OGFC layer on top of that. Travis, can you go back one? Thank you. As I said, implementing the 3/8 inch SMA gave us more flexibility when it comes to keeping the pavement preservation as an option. Because we didn't have to mill that extra inch, we were still able to save that 0.8 inches of asphalt, and that prevented us from having to put that extra inch of asphalt to replace the entire layer. That inch of asphalt, by our measurements, 111 pounds per square yard, 28 feet wide. We ended up doing that to the inbound and the outside lane and the 4-foot inside shoulder. The contract price for the half an inch SMA, which is what it would have been otherwise, was $123.58 per ton contract price. So having this 3/8 inch SMA gave us the opportunity to save $600,000 on this mix alone, which can be applied somewhere else in our system. Opinions. Having this 3/8 inch SMA for ALDOT gave us more flexibility in project scoping. The more flexibility, the more toolboxes the more tools we have in the toolbox lets us stretch our dollars more and lets our road network be more healthy. That's going to be more and more of an issue moving forward, as it always is. We never have enough money in our interstates and our highways. That's just how it always is. So the 3/8 inch SMA filled a gap that we needed as a state, and we have had success with it so far. And that's pretty much all I got, other than the questions. That's my contact information.
Thanks, John. We appreciate it very much. Can you hear me again?
Yes.
All right, good deal. One thing that I'll add about that interstate project, and John, you and I didn't debrief ahead of time, but so correct me if I'm wrong, but that if you're thinking about that the SMA thin lay versus a dense graded thin lay, you get a little bit of macro texture in the SMA thin lay, and I think that gives y'all the option of leaving it exposed to traffic over the wintertime without worrying about the risk so much of wet weather accidents. So like if somebody is participating in a webinar and you're thinking, well, you could have used a dense graded thin lay 475 mix to underneath that OGFC on the interstate, well then you would not have the option of leaving it open to traffic in cold weather until you got enough temperature to put the OGFC on top of it. So I think that's that's one of the important things, and that might actually be on my takeaway slide regarding what kind of value that mix provides to you. So I'm gonna kind of like we traditionally do. I've got this one slide that's got kind of my view of the takeaways, and then we'll do some question and answer that'll be moderated by Travis. And Travis, I tried to answer some of the simpler questions in the chat as we were going through, but you may want to revisit some of that stuff as a function of the time that we might have. But as I said earlier, we've had really positive track experience with the 9.5 first, and then the 4.75 en masse thin lay SMA. They've both done really well. So the SMA positive SMA performance, we kind of think we got to load these mixes up with rock to get that good SMA performance, but you can get good durability and good performance with the smaller size materials as long as you still produce the stone skeleton or the aggregate skeleton that makes that mix, and the good film thickness that makes it such a good deal. And as I mentioned, this gives you a little bit of macrotexture. You have very low macrotexture with the small en masse dense graded thin lays, but because this mix is really non-heavy and gap graded, you do get some macrotexture with it, which is going to help you with wet weather accidents. So when you get into stage construction like this interstate project that John mentioned, if it does end up, cool weather catches you and you can't place the SMA or the OGFC surface, then you can keep that under traffic on the interstate without worrying about spikes in wet weather accidents. There was a question in the chat box about fibers. We did put fibers in this mix, but at the time that we ran it in 2018, it was the only mix that we put on the 2018 track that needed fibers. So rather than mobilize a fiber blower and have all the logistics associated with that, we use this as an opportunity to try a product that it was pelletized fibers that were provided to us, and we just added the pelletized fibers on the wrap belt because this was a 20% wrap mix, and then we did see really good dispersion of those pelletized fibers, and we used that to control drain down when we were producing the mix. We also had a question about filler, and we did run 5% flash in this mix, and that gave us about a little over 10% on the passing the 200 with what we produced in the plant. The whole idea with this test section, as Carolina presented, was to have a relatively thin structure for our 20,000 pound axles here on the test track. So we would relatively thin structure, so we would have some good deflections, but then we use the Hyma binder in everything below the thin lay so that we could really get a lot of excitement in the thin lay, good deflections, a lot of movement. And then that way we felt like we could really put that to the test as a possible high performance preservation tool. And we've done that with other test sections. We did that in the cracking group experiment that we ran here for 2 research cycles, just so that we could isolate cracking to the surface layer. That's the same thing we did here in this test section. As Carolina mentioned, we did see a dramatic increase in smoothness just with the 3/4 inch thin lay. The other section that's in this study is a 1/2 inch thick dense graded thin lay, and in both cases we saw roughness go from, say, 350 inches per mile down to the 150 inch per mile type zone, which is that's not a very smooth pavement, but we consider it to be acceptable for the track. And the thinking was that just with a thin lay with that much roughness, eventually the roughness will reflect, and you might start out smooth, but surely you're going to lose that over time because it's just a thin lay. But we've not seen that at all. As you saw in the roughness data that Carolina presented, it's very flat, it's very stable. And so, that I think that's an indication of good mix quality. It's not moving around at all on the mat. Otherwise, the roughness would reflect. One of the things to point out here is if you're doing like the 1/2 inch thick dense graded thin lay or the 3/4 inch thick SMA thin lay, you've got to have a uniform enough cross slope when you put this mix down so that you're not going to drag the screed. When you have a milling project like what John talked about, their use of it on the interstate, that you're milling so you can mill in the uniform cross slope. But if you're just using it for straight up preservation and all you're going to do is go out there and use it as an overlay, if you've got deformation in the wheel pass and kind of an irregular transverse cross slope with really thin lifts like this, you are at risk of dragging the screed. So you need to make sure that you've you've got enough of a uniform cross slope so that is not going to happen. A big part of this is you got to have buy-in to do this from the aggregate industry, because you end up having to produce number 9 material as a standalone stockpile. So, you know, instead of producing 8, 9, 10s or screenings or 89s, you've got essentially a single size fraction aggregate that it takes to do the gap grading in this mix design. And that's a big commitment from the aggregate industry, you know, and that is where a lot of the cost per ton for this mix is coming from. But, you know, it's rich, it's got a high asphalt content because it's an SMA. But on the aggregate side, you know, it's that material you're gonna pay more for it per ton on the virgin aggregate side, because it does require extra processing, and then it does kind of mess up inventory management for various size fractions. So it's important to work, if you want to do this, communicate with the aggregate industry on the front end to make sure everybody's on board with this material being available for your use. Of course, our thinking and our focus in this was all about preservation, but you know, the reason why we wanted to bring John in here and get him to talk about their policy and their process and why they picked this mix on the interstate is because it's a really good example of targeted use of that mix to meet a very specific need. You know, so that they used it to reduce the amount of material they milled out and put back in, and still achieve a high level of performance and essentially a good platform for the OGSC that they're putting on the surface. One of the things that I like about this mix, and Tim Ashenbrenner is in this web meeting, you know, we're chatting earlier. If you're using this for preservation, and you're you know, just doing an overlay on a road as a high performance preservation tool, because this mix has straight 9s in it, you do have the option as you like pave into a curve maybe that has an odd intersection or a short stopping distance or some reason why you have a high accident rate in a specific location. You actually can substitute calcined bauxite for 9s at the asphalt plant and kind of turn this into an enhanced friction asphalt surface, and then just kind of run out of it and transition back into your mix design. So the fact that it's a heavy number 9 material mix kind of creates that option for you, and I like that, you know, because we're doing more and more research at NCAT and in other places on how can we use the, you know, maximum use of locally available material, but at the same time hit our minimum friction requirements or hit enhanced friction targets for specific locations. And this mix is a great example of getting a little bit of macro texture out of it. And then you can easily substitute calcined bauxite and turn it into a good enhanced friction surface. So I think I cut John off when I stole the screen share, but that's his email address. I apologize for that, John. I jumped the gun a little bit, but that's my contact information, and then Carolina and John, and you know, hopefully we can address any questions that you might have here before we get finished. But if not, feel free to follow up with us, and we'll be very happy to help you any way that we can.
So one of the questions that's come in a couple times from a couple different people that I want to give John the opportunity to address is, was there any permeability testing done with this SMA mix? So somebody thought maybe they heard that you were concerned about permeability, and somebody else just asked straight up if there was testing done.
We were not worried about permeability for this particular mix. The permeability issue we had previously was for a much larger mix. It was the 3/4 inch SMA that we normally just use as the SMA binder, like underneath the wearing surface. So we did not treat this any differently than we would a normal wearing surface.
Sure.
And I had reported in the chat box earlier that we got right at 94% density when we put this stuff down. So, you know, my expectation is that you're going to measure near zero permeability if you go out there and set up and test on it. So that I don't think that's going to be an issue at all.
Yeah, I think so. I think one of the other things I didn't quite hear, Buzz, I didn't quite hear you mention it, but there was a lot of friction testing done. That was a question that came up there, looking to both see if we had micro and macro texture out there. So typically our setup is that we're out there doing the locking wheel trailer tests on the track. We're also doing the dynamic friction tester, And Buzz, I think I saw you mention that the British pendulum was done on the raw aggregate as well.
Yeah, and these were all materials that are in ALDOT's aggregate control program. So these are very characterized sources, and BPN is a big part of that. But oftentimes we think, well, we got to have really high macro texture because that's what that's going to provide safe friction numbers. But the problem is that as I said in the chat when I was talking to Tim, you can have super high macro texture, but if you don't have good micro texture, you're not going to have good friction numbers. And the fact that we have good friction numbers on this mix is an indication that we do have good micro texture. But as Travis said, we do several different types of friction tests out here on a regular basis, and we feel really good about the safety of this material. But it's got a little bit of granite in it. You can go to the track website and download the performance reports and construction reports, and it's got 20% wrap in it that's a fine fractionated wrap, because of the size of the mix. But that's probably got a lot of granite in it too, so there's a significant amount of granite in the mix that I think provides the micro texture that we need to get good friction numbers.
Okay, great. All right, given the time, I'm going to go ahead and shut things down at this point. I want to thank everybody for joining us again for our NCAT implementation webinar series every month, the third Thursday. So on November 17th, we're going to have our next installment. We're going to talk about the Arizona rubber gap graded mixture that's used for durable and crack resistant pavements. We're excited to see you all back again then. And until then, we want to make sure that you all have a wonderful time. So thank you all for joining.
Hey, everybody have a blessed day. Thanks very much.
See you next time.
Thank you, John. Thank you, Carolina. Bye-bye.